Let's start. Okay, Admiral, welcome to Seattle. At least,
Thanks.
at least
It's
virtually.
it's really hot and muggy in Seattle, at least my version of Seattle.
Well, it's pretty warm. It's in the 80s today. Um, you were going to be here for Fleet Week for Seafair, but that was canceled because of COVID. So this is the best we can do, I guess. Um, so I thought our conversation today could be about to give folks in our region some insights into the Navy's role and capabilities and environmental modeling and forecasting. But I thought maybe just to start off, maybe you can talk a little bit about your own background. That I think people
Okay.
would be interested in that.
Yeah, that's great. Thanks. Yeah, so John Okon, born and raised in Syracuse, New York. So I'm an upstater. I'm used to a lot of snow in the winter. Youngest of five boys. I went to school in New York City at State University of New York Maritime College for meteorology and physical oceanography. I graduated there in '91. I was a ROTC there for all 4 years. And so I went right into the Navy, drove ships for a few years. And then in 1995, I came across a couple of really young sailors, great sailors, aerographers, mates, forecasting the weather and ocean for the Navy. And I got indoctrinated in some insight into naval oceanography. Then it was naval meteorology and oceanography, but basically it's the community that I'm in now. And so I've been in the Navy since '91, been in 29 years. Been in the community 24 of those 25 years. I've got a master's in meteorology and physical oceanography from Naval Postgraduate School and National Security Studies from the Naval War College in Newport. My community is about 2,500 people around the world, about half civilian, half military, in 60 different locations. We do meteorology, oceanography, precise time, and astrometry, not astronomy or astrology, but astrometry.
Which is?
It's looking at the stars, mapping the celestial reference frame, and using it for terrestrial purposes.
Right, got it. Okay, well, great, thanks a lot. Well, let me ask you a few questions, okay, and we'll go from there.
Okay.
There's so many people that are interested in the environment these days, and the Navy possesses enormous capabilities to observe and monitor the atmosphere and the ocean. So can you tell us a little bit about how does the Navy use atmosphere and ocean data in its mission? I mean, why is being able to observe well the environment really important for the Navy?
So a lot of what we do in the U.S. we do in the Navy also. We just do it around the world in places where we don't have national assets. So yeah, we write normal 5 to 7 day forecasts, make sure that you know when to bring your coat, when to bring an umbrella. But the biggest thing we do is we then apply that to the protection of resources. Very similar we do for severe weather forecasting or hurricane forecasting. The Navy's in a very expensive business, very expensive to maintain. And we got to make sure Mother Nature's vote that we outsmart her and keep our ships, our aircraft, submarines, and our people safe. So safety of the fleet, safety of the resources is number one for my community. What we do then with it is then it's about the application of that data to the warfighting problem. And that's talking in general, not a ship sails, an aircraft flies, or a submarine get underway without naval oceanography, naval meteorology and oceanography's data. It helps us pick the right weapon at the right time, at the right location, and at the right time that we choose, so that we have a military advantage, so that we can protect our nation's interests around the world.
Right. Can you think of any concrete examples where better weather information or ocean information has made a difference for a U.S. military operation? I mean, the idea that one that comes to mind for me is D-Day, where having a better forecast was really important, right? But are there more contemporary examples of where weather was really important?
Yeah, absolutely. And so obviously D-Day is the most famous, probably the most famous weather decision that shaped our world. But so just recently, we've upgraded our numerical mesoscale model to be able to follow. It's locked on top of all of our aircraft carriers and all of our large deck amphibious ships. So this is a mobile mesoscale model. that gets initiated by our Naval Global Environmental Model, sort of our barge model. And wherever that aircraft carrier goes, it has a gridded mesoscale model over it.
Right.
Now you couple that with, we have the capability to take 3D air search radar and convert it to Doppler weather-like products on all of our large deck amphibs. So think NexRad. We have a very rudimentary version of NexRad. It gives us very similar things: composite reflectivity, rotation, vertical velocity, vertical winds. And so in areas where we operate and there's severe weather, understanding where those thunderstorms are, where those wind shear lines are, really hard if you don't have a mesoscale model with that type of sort of 1.5 kilometer resolution around it. And so just recently we had an aircraft carrier conducting flight operations overseas that without that mesoscale model and without that Doppler radar together, we would not have been able to safely get a number of jets, a number of aircraft safely on board. So think the same thing with maybe SeaTac, right? Hey, vectoring the planes into a higher altitude while the storm front comes through. Maybe Seattle in a storm front maybe is not the best example, but maybe New Orleans when we get these sea breeze fronts that kick in.
Right.
And so we use them very tactical like that. Again, safety of flight. Another more military application is, if folks recall, we had our country and really, our world had a big piracy issue off the east coast of Africa 5 to 10 years ago. And so we were able to use the conditions in which these vessels that the pirates operate on. We know that they can only operate in so high a sea state in wind conditions, that if we can model those, right, then we can start tracking pattern of life where we think they could and could not operate. And then we're able to route our container vessels and our oilers and our Navy vessels into those areas where we know the bad guys can't operate because of the limitations of their vessels. And so that's more of a tactical application. And let me give you one more. It's more in oceanography and hydrography. So understanding bathymetry is the topography of the ocean floor. And so in a number of areas where we operate with our friends, charts are 60, 70 years old. And as the chart decreases, the chart age gets older, and your uncertainty in hydrography or bathymetry grows, that has a direct relation to the cost of insurance for a ship to go into that port. So what we can do is we can go in my community, we have multiple ways of going in, whether expeditionary or with a capital oceanographic ship. We can go in, map the bottom of the ocean, right, which then gives us a better understanding of how to ingress and egress into that port. But it also then does some nation building by giving that chart to the host nation, where they can go to someone like Lloyd's of London, update their chart, and then that helps decrease the insurance rates, which then helps the economic prosperity of that nation.
Yeah, interesting.
So it's sort of a broad scope from protection of resources, aircraft, all the way to nation building and building partnerships.
Right. Well, when you think of the U.S. military, you think of high-tech stuff. And so one thing I'm curious about, how does the Navy collect weather and ocean data using really high-tech approaches, like unmanned drones and things like that? Can you tell us a bit about that?
Yeah, in the atmosphere, where most of our, almost 99% of our data comes through satellites, just like National Weather Service or independent forecasters. Right. The satellites are so good now with multispectral channels, IR, Viz, you name it. It's really, really high end. In the ocean, it's not the same, right? Our world's covered by 70% of water.
Right.
And if you look at the data density, I did a study. You look at the data density in the ocean, it's the same data density that we had in the atmosphere in the North Atlantic back in World War I. So we're about a decade behind where atmospheric data is. And so we use unmanned systems. All of our ships, all of our submarines have the ability to measure salinity, temperature, and pressure, which are are the three key parameters that give you a sound velocity profile. We have expendable bathythermographs, air launched and surface launched. And then in my community, as a leader of unmanned systems, we operate a fleet of about 200 unmanned systems, all the way from surface unmanned that collect hydrography, weather, and physical oceanography, sea surface temperature, salinity temperature. But then we have ones that go all the way down to 6,000 meters that can collect that same type of data. And so what we obviously, with only 200, we also use profiling floats. And I know I talked to your team yesterday about this. These are long-term, persistent, part of the Argo network, can stay out there for years, collect anywhere from, 5 to 10 days, depending on your sampling rate. We use those a lot. But these not only profiling floats, but these Slocum gliders, it's a type of glider that we use. We put them in areas where there's large uncertainty in the ocean, whether it's large temperature variations, whether it's a location of an eddy,
right,
or location of a current, or there's physical processes going on that are changing the dynamics, which in fact, what we're worried about and most concerned about is the sound velocity profile, how acoustics travel for our submarines. And so we use unmanned systems, and it's grown. Even my time as oceanographer, we continue this not linear growth, exponential growth, not only in our community, but then leveraging our partner nations and our industry and academia friends that are also doing the same thing. The UNOLS fleet, whether it's Scripps, Woods Hole, Oregon State, University of Southern Mississippi, they have ships out there and they're putting similar sensors in for academic purposes, but then I can then leverage those into the Navy for military purposes.
Sure. Well, I'm in the educational business. I'm in the STEM business. So a natural question for me is, what kind of opportunities does the Navy offer for, science, technology, engineering students, STEM students, to solve environmental and prediction problems?
Wow, it's a blank sheet. Whether you want to come in enlisted, you want to be an officer, or you want to be a civilian. And like I said, my community is about 50-50 military civilian. On the civilian side, we work at tough problems, not only in the atmosphere, but in the ocean. And I've got chemical engineers, mechanical engineers, mathematicians, physicists, astrophysicists, oceanographers, biologists, geologists. If it's a STEM degree, there's a real good chance that you have space in my community.
Yeah.
Now, on the military side, both officer and enlisted, we really have two opportunities. On the enlisted side, it's the aerographer's mate, and they're a full spectrum forecaster. We give them really intense training, 2 different schools, and they're a qualified, a WMO qualified forecaster.
Right.
And so they not only forecast the ocean, but the atmosphere. They go from the bottom of the ocean to the stars. On the officer side, highly educated. Now we do focus our officer education when we bring them in on STEM, right? We want to make sure that they have a, calculus-based physics. They got physics. They've got math. But we educate all of our, I'll call it mid-grade officers, folks that have 8 to 12 years in the Navy that are going to sort of stay Navy long-term to 20 or more. We send every one of them to the Naval Postgraduate School for a 27-month in-resident, fully paid, fully funded master's in meteorology and physical oceanography. And as I mentioned, that's where I went. I graduated in 2003 from there.
Sure. I know a lot of people there. And we've had some Navy ROTC students going through here at the University of Washington, of course.
Yep.
Sure.
Do you know Dr. Wendell Nuss?
Extremely well.
Yeah. Dr. Nuss was my thesis advisor.
Well, he went here, and so we know him very, very well. So
if I could, I did some time on a ship off the East Coast, and one of my last deployments coming back, the CEO of the ship wanted to get us into port before Thanksgiving, but there was also this thing that I didn't really understand until I went through, and that's the North Wall effect.
Yeah.
Very steep, high amplitude, high frequency, very destructive waves that sets up off the western boundary currents and very prominent on the Gulf Stream.
Sure.
And I went through 20 to 24 foot seas for a period of about 8 hours. And so when I converted to meteorology and oceanography officer and I went out, I was in Dr. Nuss's trope and strat class, and then I did a coastal meteorology, and I went with him to this idea. Hey, sir, I'd like to really study this phenomena and try to get some forecasting rules so that our forecasters can really understand that the trajectory of the cold air outbreak matters. The angle it comes off of the eastern seaboard, off of the capes of North Carolina and Virginia, the depth of the cold air along with the temperature. And so I used coamps back then, and I think I actually ran some NORAPs, which is, for folks that know, that's the predecessor for coamps. I ran some mesoscale model, and we came up with some thumb rules. Really good. So I hope you Google my name and Google Northwall and read my thesis and give me a grade.
Sure, and Wendell Nuss was a graduate here from the University of Washington. So in some ways, you're a descendant here from the Husky tradition. Let me ask you one final question, just looking to the future. What's the Navy's long-term vision in collecting environmental data and prediction? I mean, where are you going over the next 10 years or so? Can you give us any insights into that?
Yeah, I'd love to. And so we are in this for the very long game. The ocean and atmosphere absolutely matter to the long-term prosperity and protecting American way of life. And so we're making some very, very targeted investments on our environmental, our atmospheric model. Our ocean model, HICOM, is world-class, and we protect it as such. On the operational atmospheric model, we've been working with NRL and NPS on the Neptune model and the NUMA core. And we believe that's the way of the future. A non-hydrostatic global model that has both temporal and spatial variability that can allow us to use supercomputing a little bit better, scale it a little bit better, and then drive down that resolution where it matters to naval forces and joint forces. And so that NUMA Neptune core is really the center focus of our operational modeling plan. The other thing we're trying to do is squeeze as much information as we can out of the model. There's a lot of information in that data that I don't think we're really looking at hard, specifically in the electromagnetic, electro-optical realm that I think the information's there, talking to Dr. Hansen. And so we're making more of a targeted investment there to see if there's a little bit different ways of looking at the data to help us be a little bit better and a little faster. And so the one thing that when we look at data, and you've heard me talk about decisions a number of times, we have this concept called the battle space on demand. And it's all about driving data to decisions. If we're collecting data just for data's sake, we don't have the resources to do that. Everything that we do is done with very good purpose, or sharing a data with our industry, academia, and foreign partner nations. And that's about driving data to decisions. But the amount of time that we spend in data collection and prediction right now is a lot. And so when we talk about that cycle, we have to try to drive that speed faster from data through prediction, so that we can get in the hands of decision makers earlier to do exactly what I talked about when I started: pick the right weapon, the right location at the right time. And that means maybe changing the decision based on the outcome and what the environment's showing us.
So what do you do about security? I mean, that's a big issue, right?
It's huge.
Our nation's dependent upon the integrity of our forecasting and observing systems. I mean, what are you doing to protect us from hacking and those kind of issues?
Yeah, so when I first came in the Navy, it was all about physical security, right? You wanted to look at fence lines, guards on the gate. That is very important still, but there's an adversary out there that we can't see, and they operate in cyberspace. They're on our computers, and they're trying to steal our intellectual capital, our data, and our modeling code. And so cybersecurity is absolutely number one for me. Cybersecurity is the new operational security. We have to be able to protect our intellectual capital across the board. And people are out there right now. I can tell you in my community, people are out there right now trying to steal what we have built over centuries of intellectual capital and code to give us the advantage in the environment. Yeah. And so cybersecurity is really cool. And that's why, I get asked this question a lot. Why is the Navy running their own models? Because we have to have that assured numerical weather and ocean prediction at all classification levels. And we leverage our partners in academia a lot.
Sure.
We talked about it yesterday. So Dr. Lou Cellini at National Weather Service, great partner. NOAA, NSAP, great partners. Air Force, great partners. But when our nation needs their military to fight and win for them, it's going to start just like it did in D-Day with the forecast. Right. Can my forces get there? Do I have the advantage? And if we don't have that assured predictive battle space awareness, that prediction, then the enemy's going to know more truth about the environment, and we're probably going to lose.
Sure. Well, with D-Day, it's us acting when the others thought that the weather wasn't good enough to act, right? Mm-hmm. So that was important. Well, Admiral, thank you so much for talking to me this afternoon. It's a shame you couldn't come to Seattle, but maybe for next Seafair or some other time. So thank you very much. Really appreciate the opportunity.
Thanks, Dr. Mass. I appreciate it. And go Navy, beat Army.